Yeah, pen's kind of fat, huh? I was just noticing that. Just Fe2O3. I thought I changed those. Oh, here we go. That's the one I want. Okay, the other thing that you can have is you can take a solution. Now, a solution is what? It's a homogeneous mixture. Okay, so if you have a homogeneous mixture, anybody know how you tell it's a homogeneous mixture?
One element or
No.
throughout?
Same throughout, but how do you tell, like, when you have a homogeneous? There's nothing in it. You look at it, it's clear. All right. So when we say it's a homogeneous, if you can see stuff in it, then it's not homogeneous. Right? So like if you take, you go to the doctor and you get amoxicillin when you're a kid and it was always that pink nasty liquid, that was not a homogeneous solution because you couldn't see through it. And if you let it, what do they always tell you to do with it? Shake it. All right, keep it in the fridge and then shake it before you take it because it's not homogeneous. It's settling on the inside. It's just suspension, actually colloid. It's a suspension of particles in a liquid. Okay, so for something to be homogeneous, it has to be clear. It could be yellow, like when you go to the bathroom. That's a homogeneous solution. Okay, well the one is, the two's not. But I don't know if I have to explain that. But yeah, so homogeneous mixture. It's clear. So here's the thing: if you take two solutions and you mix them together, and then a solid comes out of that. That is, it becomes opaque. You can't see through it. It's not clear anymore, right? That's the sign of a chemical reaction. So solids form, right, from a clear solution or mixing of clear solutions. Let me do this from mixing. And I'll put that plural. That makes more sense. The other thing that can happen, and this is not always true for this one, is that you can have gas form during a reaction. And so what are the signs of that you have a gas formed in a reaction? How do you tell?
Bubbles.
What's that?
Bubbles.
Bubbles. Yeah, that's the best way. All right. What's another way? How do you tell that a gas is formed? Huh? I heard something. Steam? No. That's like a... Okay, watch this. How do you know when somebody has gas? Yeah, you don't see it, right? You smell it. We say odor, right? Smell implies both different kinds of things, but yeah. Yeah, there's a smell. And oddly enough, like the ones that most commonly happens in the labs really smell bad. I mean, they smell like what you're used to smelling, I suppose, when somebody has gas. You could also have light. I don't think I have to tell you like how you know light is formed in a reaction, but a light stick, like a glow stick, right? That's an example of a chemical reaction that you could tell that's going on because of light. And temperature change. How do you know something has a temperature change?
Color?
Color?
Bright red.
No. Yeah. How does it feel? If you have a chemical reaction taking place inside like a beaker or a test tube, yeah, it feels hot when it gives off heat, right? Or it absorbs heat. So it's temperature change, the way you tell. Like this list is great, except it doesn't tell you how you know those things are going on. Now light's obvious, it creates light, you see it, right? But there's a temperature change, and so it feels hot. Or cold. That it's different than room temperature. Okay. So that's how you tell that there's a chemical reaction. So these are the ways that you can tell there are different kinds of chemical reactions. You see the change in color. You can see the solution become cloudy, right? You could smell things. You see bubbles formed. Lights, like I said, self-evident. And then it feels hot or it feels cold, right? That's how you know. And sometimes it's real obvious, and sometimes it's real subtle. And so you have to pay attention to things as you're doing them in the lab. So when we write a chemical reaction, we write them like this. This might be, oh, I started balancing it. I don't think I finished it. Yeah, I didn't finish it. Where did I? Maybe I did. I don't know. Can't tell you. So this is how we write our chemical reactions. And then I listed all the parts down below. So this is I. This is the reactants. And this is the products. You could write reactants or products, but I was being lazy, so I'm just writing the letters that correspond to them. Now, there's the reaction arrow, and there's a lot of different things that can be here. So for example, you could say you have to heat the reaction to make it happen. That's a very common action. And this symbol, that's for heat. I'll make that into the 1 like I used in there, like a Times Roman 1. Ooh, that's an ugly looking 1. That's the symbol for heating a chemical reaction. It's just a delta, okay? Sometimes they'll list reaction conditions. So they'll say like 80 degrees Celsius. I'll just put that under here. And that'll either be written on top of the arrow or on the bottom of the arrow, okay? Delta could also be at the top or the bottom as well. So these things could be top or bottom. So if you saw 80 degrees Celsius, that means you'd have to heat it, but there's a specific temperature that you have to get it to make that reaction happen. Okay. We also have chemical formulas and the states. I won't point those out because you can see those up there. And then we have to have mass balance. When we have a chemical reaction, the numbers of atoms on each side of the reaction the numbers of each type of atom on each side of the reaction have to be exactly the same. So we use something called stoichiometric coefficients. I'm going to write that down here. Gosh. Kind of like Monday all over again. Except for Monday yesterday was actually pretty nice. I don't feel like I've talked to people for a week.
Good thing.
All right.
That's what makes it feel really nice.
It's quiet. Go to a baseball game, talk nonsense.
How many kids do you have there?
There's 6.
That explains.
3 are out of the house, but they came over and we had Valentine's Day and other things. Out of the house, yeah, they were still around. But my second oldest son came home, and he goes, "Yeah, I noticed when I come home now it's really quiet. Like, it's because you're not here." a lot of stuff going on all the time in our house. And for us, the house is quiet, and there's 3 people, like 3 kids. There's 5 of us. That's a quiet house. It's weird. It's getting quieter and quieter. Okay, so let me explain to you what that means, stoichiometric coefficients, in a second, by showing you through this reaction. So what I have on the left-hand side, you notice there's 3 carbons. I have 3 carbons, so this is the coefficient. This is VI. That's the stoichiometric coefficient. That thing multiplies through. So if you think about it like an equation, like there's parentheses around this whole thing, I'm multiplying that whole thing. So how many oxygens are with that carbon, those 3 carbons? 6, right? So this is 3 carbons. And then I have 6 oxygens plus I have water over there, right? So my H2O, there's not a coefficient in front of it, but it's an implied 1. We don't write the ones when we multiply, right? So it's an implied 1. So the hydrogens, there's 2. And then for this is for the water, from the water. And then there's a 1 here because that one's from water too. If you look on the left-hand side, right, I have 3 carbons. I have 6 hydrogens, and then the oxygens. Well, for the oxygens, I have 1 from the molecule is C3H6O, right? And I have, how many here? O2 times 3, right? I have 6. It's a total of 7. And you'll notice I have the same numbers of carbons and hydrogens on each side and oxygens on each side. This is what we mean by the equation is balanced. So when we say mass, the equation is mass balance, most of the time people just say it's balanced because we have the same number of atoms that we started with and the same number of atoms that we ended with of each type, right, and in total. So one of the things that you have to be good at, because this is going to be super important for like the rest of all of your chemistry life, whatever that happens to be, you have to get good at balancing equations. So we're going to do some. And I made a list of things that you should pay attention to, right? It says balancing a reaction is a process that results in a chemical reaction in which the atoms of each element are mass balanced on each side of the reaction. What does that mean? It's just the same number. That's how we say it. So, and we call that a balanced reaction. So some suggestions, right? You're gonna get the questions. Sometimes I will give it to you like this. You don't have to write anything as far as formulas go. They're already written for you, okay? So write the products and reactants correctly. This is like the thing that you always fall back on, because when you get a name and you write the formula, if you can't balance it, you probably wrote the formula wrong. You have to double check it. Okay? The other nice thing is you can always tell when you're right because you just add everything up on each side and make sure it comes out. And there's only one way to balance most reactions. Okay? Here's the other thing. There is really no like fixed way to do it. So people like that, some people hate that. They want to know, like, if I could start with this and I can make my way through it, life will be smooth and I don't have to think about how it's done. That's great. And then there's other people like me, like I don't like rules very much and I just sort of make it up as I go along. But then there's some things you can't do that way. But here, there's not really any one way to do it that's correct or completely correct. So here's my suggestions to you when you do this, right? When you're balancing, you're going to start with whatever looks like it has the most stuff in it. Okay? That's the thing you want to focus on, balancing, because when you balance everything in that most complicated molecule, then you've balanced most everything in the reaction. So that's the place you want to start. That is already vague, like what is the most complicated, what has the most stuff. It doesn't matter, you just pick one and that's where you start, okay? Because remember, there's no fixed way to do this. The other thing that I recommend to people is if you have a polyatomic ion, which means you got to know the polyatomic ions, okay? Don't break them up while you're balancing. Most of the time in the reactions that we're doing, they travel together like as units. Other suggestions that are helpful, right? Leave pure elements for last. And I'll show you why that is in a second. And then don't worry about states. It's just a lot easier to balance. The states don't matter in the balancing. Every reaction you see in the book will probably have states with it. Just ignore those and balance without them, add them back in later, okay? All right, so we're gonna balance a reaction. So in that first reaction, what looks like it's the most complicated, has the most stuff in it.
Cobalt,
Yeah, cobalt nitrate, right? So this looks like it has the most stuff in it, so I'm gonna put a line underneath here. Now, I used to teach this a whole bunch of different ways, and I think I've settled back on the way I learned how to do it like a billion years ago. Okay? 1,000,001, I don't know, it's a long time ago. So this is what I'm gonna do. Everything that's in that formula, I wanna balance on the right-hand side. So that's the reactant, right? It doesn't have to be a reactant either. It could be a product that's the most complicated. But I'm gonna start with the reactant in this case. I'm gonna say, well, I have one cobalt, right? How many cobalts do I have on the right? So far, so good. This 2 applies only to the parentheses, right? How many nitrates do I have? 2 on the left, right? There's 1 here. So I have 1 here. So I checked it off. It's done. How many nitrates are there? There's 2, right? How many KNO3s do I need? Right? So on the right-hand side, that's where the nitrate is. Do you see that? How many of those do I need then? 2, right? So the way you do it is you use a coefficient. You got to multiply the whole thing because the nitrates only come with potassiums, right? So now I've done this part. And most everything in the reaction is already balanced. And so what I have to do now is balance this. So I make sure I go one thing at a time, right? How many sulfurs are on the left? How many on the right? All right, so that's done. And I'll tell you what, if you're left with the last thing, the last polyatomic ion or element, it better be balanced, because if it's not, what does that mean? You start over, yeah. And if it's one where you're given names of formulas, you go back to the formulas and you rewrite them. But otherwise, you don't mess with them. Once you have them, you have them. How many potassiums on the left? How many on the right? You're done. That's it. Make sense so far?
What about the oxygen that has like a 3 and a 2 subscript, and then you got a 3 on the right? So that coefficient.
Yeah, so let me ask you a question. That's polyatomic ion nitrate, right? So those always come together. N and 3 O's, right? Right, okay. So I have 2 of those. That's the way I want you to do it. Now, let me show you how you do it. Like, because you're looking at, you're detail oriented, so you're looking at the little things, right? So like you're looking at, well, there's 3 oxygens times 2, so that's 6, right? On the left side. How many are on the right side?
But then that leading coefficient, does that, yeah?
So 6, right?
6, right?
Yeah, so it does balance. Right. So, but as long as you're keeping them together as a unit, right, it doesn't matter if you keep track of the oxygen separately, which can lead to weird balancing of equations because you get multiple oxygens in different places, some with polyatomic ions, some not with the polyatomic ion. But if you keep track of the polyatomic ions and just keep them grouped up, usually that works out pretty well. And if you can't do it that way, then that's a situation where you have to break it all the way down. Okay. All right, do the next one. What are you going to start with? Yes, lithium sulfide, because it's ionic, you don't use the prefixes. Yeah. So lithium sulfide. So that's where I'm going to start with. And that's the last thing I'm going to say. Go ahead and do it. We start with the same thing, and usually people end up getting done the same way. I think I need another gallon of coffee or something. Like when you're done, you're like, no, that wouldn't. worry about this. Some of them you won't worry about. Trust me, they get hard. Well, that's good. A bright pink spot in my pocket. All right. How many sulfurs do you have on each side? One. That's done. Good. Whew. How many lithiums on the left? Yeah. How many on the right? So what do you have to do? Put a 2 in front of it. Don't change subscripts. You kill me when you do that. Okay, so those are done, right? So I have to do this guy and this guy, right? So what you want to do? You want to do the H2 or the I? Doesn't matter like which one you choose. I'll just pick the I then. How many I's do I have here? How many do I have here? Right? So what do I need? Coefficient of 2. And then we're going to check, because we got to make sure the H is balanced. You got to check everything, because that's how you know if you screwed up. You got to go all the way to the bitter end. Okay. So I did the I's. The I's are good. Now we're going to H's. There's 2 of these. And there's 2 of these. So that one's done too. So we have everything balanced. That's a balanced equation. That one's done. Okay. Like I said, you have to get good at this. You do it a lot. So for hydrocarbons, hydrocarbons is the first place you can get real tricky. And you'll see a lot of these ones. C2H6. Regardless of what you think, I'm just going to say this. You're always going to start, when you have a hydrocarbon, you're going to always start with a hydrocarbon. What is a hydrocarbon? We know what it means to be when a compound is a hydrocarbon. Like gasoline is a hydrocarbon. Oil is a hydrocarbon. What does it mean? Where do you get the name? Hydrogen and carbon. Hydrocarbon, yeah. That gets its name. These scientists are so tricky. So how many carbons do I have? Left side. How many CO2s do I need? So that's that. How many hydrogens do I have on the left?
6.
How many H2Os do I need? 3. So that's done. So far, so good, guys. Does it make sense, like what's going on here? This is where it's going to get kind of tricky. Now I have oxygen in 2 compounds, right? So what I need to do is I need to combine the totals. So here I have 4. And then here I have 3. So this is just for oxygen. I have 3. I have 4. I get 7. But it comes as 2s. Yeah, so there's a couple approaches to this. If it comes as 2s, and you can't make 7 equal to 2. You just can't, like 2, 4, 6, 8. You just skip it 7 altogether, right? But if you double everything, then it'll work out. Okay, so, but I'm going to show you another way, because that's the way I think your book probably does it. And some students will say, well, how do I know how to double it? Like, just because you have to. I mean, so let me show you. Here's the other way. You have to have whole numbers. Just like atoms, you can't have like half an atom. You can't have half a molecule. But just for the sake of balancing, when you need 7 of these, I do this. 7.5 times 2 is what? 7. If it was 0.3, it'd be 7 over 3. So this number is the number that I need still. And this number is this number here. I make a fraction out of it. Now, I can't leave it that way. But the fraction's telling me what I have to do. I have to double everything. And so you can either presume that you double everything. But if you have to triple it and you double it, you're going to be in the same boat, right? So you're going to have 2. So at the end, I'm going to multiply everything by 2. And I'm going to 2C2H6 plus 7 O2s, 4 CO2s plus 6 H2Os.
So then when that happens, you do whatever the subscript says?
Yeah, basically. So if it was an O3, because there's lots of reactions we do with ozone. We use ozone for purifying and cleansing and all kinds of stuff, right? You'd multiply everything by 3 just to get rid of that oddball oxygen. I'm letting her think. That makes sense?
But
What's bugging you?
why do you have to double it? Like,
Oh.
because you said that it's because of it's your
So
own
oxygen comes as 2s, right? O2. But I need 7 on that side. So think about it. 2, 4,
Oh,
6,
Oh, okay, like 8.
8.
I get it.
All right, you do the next one. That one's actually a little nicer. Again, combustion of a hydrocarbon. Uses oxygen, same product, CO2 and water. Oh, I didn't check it, but that one's correct. You need to, when you're done with this step here, you still double check. So there would be like 4 carbons, 12 hydrogens, 14 oxygens that we compare left and right side to make sure it's balanced. Do the next one. Done yet? All right. And raise your hand if you have questions on it. Yeah. Yeah. And then double it. Actually, do the next 2. And then I'll go ahead and walk through them. Yep. Let's see. This is just some of these areas. 1, 4, 3, right? That's 7, right? But there's 1 here. So you subtract that off. So you need 6 more, is basically what you need. How many of you guys learned to balance reactions a different way? Have anybody done this before? They usually teach you atom by atom by atom. They have to count everything, or is this the same way that you learned it? What's that?
I don't remember.
Don't remember.
Yeah, I don't remember either. I think it was more difficult. Because they were like,
Yeah, and then they say like you got to count every single atom and every single compound, and I'm like, we do not do that in real life. It's gonna don't. We like being efficient. Okay, so I'll go ahead and do this one, and then you guys can continue working on the lower one. So again, I'm going to start with all hydrocarbon problems. You start with the hydrocarbon. This is a hydrocarbon with oxygen, but yeah, it's a hydrocarbon with oxygen. So I'm going to have 2, right? And then what do I need? 3. So what does that give me? Yeah, 7, right? Gives me 7 oxygens. Now I did this and this and this than this, right? So basically what you do, I did is I balanced everything that I could in that compound with everything on the right. That's where you're stuck right now. And I noticed a couple of people were actually stuck there. So I need to have 7 total. You notice I haven't done anything with this one yet. So that means I can subtract that off the total that I need. All right? So 7 minus the 1 I have, that means I really only need 6. So I can just drop the 3 there. And then when you do that, we can double check. There's a 1 plus 6, that's 7, right? And that's the 7 that I have on the other side. So I subtracted the 1 I already had away, and then I figured out how many more I needed. All right, go ahead and do the next one. We're still working on it. And then ask questions. What? What?
Hold on, I need to.
It's the same. See, you know, it's the same. So it's 4 from here, 3 from here, so it's 4. So I just kind of just said it because it's exactly the same thing. But the difference is I'm not here.
Right.
Right. So that means I only need 6. No. Yeah, we just leave this one last. If you could have 3 here, then it would work out to 7. Yeah, you have 3 there, 4 here, that's 7. Well, you really only have just 1. Yeah, you have 2 and 1, but you can change this stuff. You can't change that.
That's what you.
Yeah, I subtracted off the 1 that I couldn't change. I couldn't change that one because it's part of the formula. If I changed that, like then it changes everything, and I'm just kind of the same. Okay. Balancing. What am I starting with? With this guy? Like compound wise, yeah? And then I could do the oxygen or I could do the chromium. It doesn't really matter, I just gotta do both. So if I do the chromium, it's 2 of them. So that would be done. And now I gotta do the oxygen, the same problem, right? I've got 3 on that side, but I have 2 on the other side. So how do you make 2 equal to 3? Like that, and then double everything, right? So that'll give me 4 CR, so I'm going to multiply that by 2, plus 3 O2s make, I don't know, 2 CR, 2 O3s, like that. All right.
You know how I did it easier? I just started with oxygen. I know you're probably not supposed to do that, but
You could have.
Yeah, and then I didn't even have to double it. I just got the 4 in the first place.
So what did you do? Oh, did you do this? Okay, there's a trick for some of these too. So this is good. CrO2 and Cr2O3. What did you do?
So I started, what did I do?
You started with the oxygen.
Yeah, I started with the oxygen.
I know what you did. I just want you to say it.
I did, so I automatically put 3 in front of O2 on the left.
Yeah.
And then I was kind of finding like a common like
Yeah.
number or whatever.
Yeah. That's
so
the
I
trick.
multiplied it by 2.
Did that,
So
right?
it's 6 on each side.
Right. Because the oxygens were in balance, so you could just cross those. And then you can just say you have 4, and then you do it. Yeah. No, I like that. That's, like I said, there's not like one way to do these. And you notice we got the same answer, right? So that's cool. There are actually, though, some reactions you have to balance like that. So it's good that you saw that. Okay, so I'm going to talk a little bit about solubility, and then do some predictions, and then we're going to do some reactions. So let's see. How far do I want to get? Yeah, let's just look at this stuff here real quick. So we talked about what it means to be soluble. Like something soluble, it makes a homogeneous mixture, which means it's clear. There's nothing floating around, no floaties in it, right? So homogeneous mixture is a solution. We can tell it's a solution because it's clear. All right. It might be colored. It could be yellow. It could be green. It could be blue. Right. But it's homogeneous. So when you have molecular compounds or ionic compounds, move back for a second. How do you know when something is a molecular compound? It's back to nomenclature, like naming stuff. I'm going to name it as a molecular compound. How do you know to name it as a molecular? You guys remember? That was all last week. Come on now. I noticed you struggled with the worksheet. I don't know if you noticed my comment.
Yeah.
You were pretty not.
When I read that.
Okay. It's, yeah, he's like pointing. It's just stuff. Yeah, it's all nonmetals. That's how you can tell nonmetals, right? And in the nomenclature, that's how you tell too. You're going to name it as a molecular when it's all nonmetal. How do you tell when something is ionic, right? It has ions in it, but it's generally a metal and a nonmetal, right? So something from the left of the stair step to something to the right of the stair step, polyatomic ions included. So it means when something is soluble and makes a solution, for molecular compounds versus ionic compounds, it means something different in terms of what happens to them when they go into solution. So when you have a molecular compound, let's say I have this molecular compound and it's CH2O, right? And I'm going to draw it like this. That's my little molecular compound. And then I have a whole bunch of them together in a block, right? So there's a whole bunch of them. Then they're making a little crystal lattice, and we're talking about types of solids. They look like little people. I'll make this one waving. Okay, so anyways, got a whole bunch of them. And when you put them into solution, and you make a solution with molecular compounds, this is what happens. There's water in here. Waters are like these guys. This is water. And this is CH2O. And roughly those are the shapes of the different things. You don't think about like liquid water, you're drinking it. It's just full of a bunch of water molecules floating around, right? When you dissolve a molecular compound into it, these guys stay together. And if you get tired of drawing, that's fine. This guy's head shrunk. That guy with his waving hand. But the molecule stays together. Remain intact. So how does that differ from like ionic compounds, right? Because I said they're different. So the ionic compound, when you look at an ionic compound, it's going to look something like this. Now, you're going to have to bear with me while I do this. Oh, actually, I don't want to make that box that big. I just want to make it smaller. And you're going to maybe not want to do this drawing and just pay attention. Those would be like the sodiums. And the chlorides would be like this. And they kind of just fill up the space in between the sodiums. Or you can think of the sodiums filling in the space between these big chloride ions. The chloride ions are much bigger. Okay. Now I'm going to put them in water. Oh, didn't let me do it. Let's see if I can do this. Oh yeah, there we go. I gotta get the lasso tool. I'm gonna cheat. I'm not gonna draw all that over again. Oh, darn it. I didn't want to flatten them. Oh well, it doesn't matter. I have to erase that. It's making me crazy. Now I don't know how to erase it. Oh, it flattened the whole thing. All right, we're gonna just do this. It's gonna just take the time to do it. I have all my little water molecules in here. Sort of random. And it's wavy on the top because it's water. And then you have this. And the ions separate. So this is Cl minus, and this is Na plus. And so they separate from each other. So what it means for a molecular compound to make a homogeneous solutions, I mean, the molecules, like it's like you go to a park with a good friend and you kind of hang out all day together, you're like the molecule, right? When you go to the park with your senior class in high school, like Disneyland, right? Everybody just takes off because they don't want to be seen with the other people that they're with. I don't know. But they all take off and go in different directions. That's more like the ionic compound, right? And there's occasionally a cluster here or there because they're oppositely charged. But for the most part, when an ionic compound dissolves, it means it breaks up into its ions. Wrong pin. Breaks into separate ions. So there's a list of rules that allows you to tell whether or not a compound will be soluble or not when it's ionic. And they're called solubility rules. Okay, solubility rules. Now, just so you know how solubility rules were created, I mean, how would you tell if something was soluble without knowing anything else? How do you know sugar's soluble? Yeah, you put it in water, you see if it dissolves, right? That's how all these rules were made. They just took a bunch of compounds that contain these ions, put it in water, and it's actually a certain amount, like 0.1 moles per liter. It has to be above it, like 0.01 moles per liter. If it's above that, then it's soluble. If it's below that, it's not soluble. So if it's not soluble, the term that we use is insoluble. So here's the way this works. This table will work. You're going to look, when you start doing this, you'll look to see what's in that left-hand column, and then you'll look to see if there's an exception and if whether or not something is an exception. I'll give you this. It's like, I'll just cut and paste this, put it on the cover page. I think you could probably already see the cover page for the exam that's coming up in 2 weeks, right? What? Huh? Like 2 weeks ago. And that was at 4 weeks. So think about that, every 4 weeks. my evil master plan, evenly space out work. What? Horrible. Okay, so we're going to figure out whether or not sodium sulfate is soluble. So look at your solubility rules, right? And where's sulfate? Help you out there. Mostly soluble. And then there's exceptions. When sulfate pairs with calcium, strontium, barium, or lead, the compound is insoluble. Like literally they took all these compounds and tried to dissolve in water. They didn't dissolve. Hey, those are insoluble. That's not rocket science. It's all empirical, which means they did experiments and they figured it out. So this one's soluble. Now, in a chemical formula and a balanced chemical equation, when we're putting states in, when we say something is soluble, we mean it dissolves in water. We would write something like this, Na2SO4, and then the state is aqueous, AQ. That means it's a homogeneous solution with water, right? Okay, what about barium sulfate? Back to the list. What? What? It's in the most usually soluble, but with barium sulfate, so this is insoluble. So we would write its state in a chemical reaction as BaSO4. Insoluble means it didn't dissolve, so it's solid. Still S. I think about it like sodium sulfate. When you're dissolving in water, the sodiums are taking off, the sulfates are breaking up into its ions, they're all floating around separately. Put barium sulfate in water, it just sinks to the bottom. It's just a lump in the bottom. Okay? Calcium carbonate. So calcium, right. What's this is the mostly soluble. This is the mostly insoluble. So if you have a carbonate, then they're generally not soluble, and the exceptions are soluble. I'll put a little note here. It means these are soluble. And these exceptions are insoluble. Okay, that's what that means. Okay, so calcium carbonate. Carbonates are generally insoluble. None of the exceptions are calcium. So it's solid, insoluble. And when you write it, it's CaCO3 and it's S. Okay, so I'm going to teach you this generally. Look at potassium phosphate. We're phosphates, right next to carbonates, right? Is potassium an exception?
Yes.
Yeah, it is. So it's soluble. So it'd be K3PO4 aqueous, okay? You will invariably at some point make that mistake where you know it's soluble and you write S because they start with the same letter. I didn't do this. It's just the way the language works. Okay. So general good things to know. It's these guys up here. If it has lithium, sodium, potassium. Right? So lithium, sodium, potassium. Notice where they're all on the periodic table. Group 1, right? Group 1 ions are always soluble. If you look at the exceptions to the carbonates, what are we listing? Lithium, sodium, and potassium. So there's so many compounds that you'll see that have a group 1 metal ion in an ionic compound that you have to figure out whether or not it's soluble. If you just memorize that, that's half your work done almost in every problem. Just aqueous, 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 right? And they don't say like rubidium, they don't say cesium, but those are all soluble as well, okay? The other one that's always soluble is nitrates, the polyatomics. And this is acetate. Right? Acetate and nitrate are also always soluble. And you'll see those, you'll see nitrates all the time in reaction. So every time you see nitrate, you just assume that it's soluble. There's a few oddball exceptions. Like for acetate, there are some exceptions to that, but for the most part, you won't encounter them here. Questions? All right, we're gonna take a break.
Sure.
Come back, have a little short demo.
Every time you tell us a hard rule, you always follow it up with most.
Yeah, it's true. Your book has this picture of 2 cups, one that has a battery and a light bulb in it, and the other one that has a battery with a light bulb that's lit in it, okay? And what they're showing is by putting sodium chloride, an ionic compound, in solution, you can make it electrically conductive and you can carry an electric current through the solution. And the result is the more ions that are in the solution, the brighter the light bulb will be lit up. So if you put a little bit of salt in there, it won't be as bright. But if you put a lot of salt in, it'll be brighter. Okay? Now, there are things that we call weak electrolytes. Oh, sorry. I meant to write weak acids. So I'll tell you the difference between strong and weak acids on the next slide, but your book doesn't even mention them in this portion, but there's strong electrolytes, weak electrolytes. Weak electrolytes make few ions. And then there's non-electrolytes, right? Things that don't make ions when they dissolve. What kinds of things don't make ions when they dissolve? What did we talk about in the last hour or so? It's soluble, right? But non-ionic compounds. What was the other kind? Molecular compounds, right? So when molecular compounds dissolve in water, they don't produce any ions, and so those are non-electrolytes. So if you did the same experiment, you put sugar and you stirred it around, you wouldn't get any light in the light bulb, okay? What do you think you would see for a weak electrolyte in terms of the light bulb behavior? It'll just be dimmer, right? Somewhere in between. So yeah, a weak electrolyte would produce something in between those two images. Okay? So the strong acids, and you have to have these memorized, they are from chapter 14. They're in these notes now. Okay? So hydrochloric acid, hydrobromic, and hydroiodic. So all the halogen-based acids except for HF. And then there's nitric acid, and there's perchloric acid, and sulfuric acid. These are all strong acids. When you put a strong acid in solution, they break up into ions. Okay, that's the definition of a strong acid. Is it completely dissociates when you put it into water. So I have HCl. It's aqueous. I put it in water with water. Actually, I'll just leave the water out for now because that's for later. And then it becomes H plus aqueous and Cl minus, and that's also aqueous. And this is 100% dissociation. 2 ions. So just like ionic compounds, they're in a class by themselves because these are actually molecular compounds that produce ions in solution, just like ionic compounds do. So these are the strong ones. Which ones are the weak ones? All the other acids in this class that you see will be weak acids. So you memorize this instead of memorizing the whole list, because there's a lot of acids that you could have. These are the strong ones. Weak acids, that's everything else. So nitric acid is this, right? So this is strong. This is nitrous acid. It's weak. But it's everything else. Literally, all the other acids that we deal with in this class will be weak acids, or if it's not like, if it's a strong acid that you don't know, then I'll tell you it's strong. Okay? All right. So I'm going to do this so you can see it. I'll just walk up into the middle. You don't need goggles for this. That's calcium nitrate. Well, we'll call it calcium chloride for today because I couldn't find a calcium chloride. It's going to do the same thing. All right, calcium chloride, and what did I say it was? It was sodium carbonate. No, it is actually sodium. Yeah, it's fine. So list. Okay, watch. I'm going to put this. You tell me whether or not it's soluble. Now you got to try mixing it. That's actually quite a bit. Calcium goes to a lot better. Nitrates, it's actually supposed to be chloride, but we'll just lie here. Nitrates just all do it all. It's not instant, right? But you see how little there is in there now? Yeah. If I keep doing this, it'll eventually all go in solution. That's what we would say. It'll all eventually go. There's a little bit left at the bottom, but it will eventually all go. So, soluble, not soluble. Soluble, yeah. And based on its chlorides are generally, it's a sodium. Carbonates are generally insoluble, but it's group 1 sodium. So we expect soluble. When you put it in water and you stir it around, it makes a solution. And you can tell it's a solution because, well, you can't see anything in it. So here's my calcium. Oh, I got a big chunk in there. Big chunks dissolve really slowly. Now, as you're stirring it, it changes the density of the solution. Because as it dissolves, you're adding stuff. The volume's not changing, which is kind of weird. Think about that. The volume, I've added stuff to it. The volume didn't change. Like, where is it going? These are kind of questions people have asked for years. Like, if you take pure ethanol and water and you mix them together, let's say you take a liter of water and a liter of ethanol, mix it together. See, that's almost all dissolved. How much do you think you end up with? Like 1.9 liters. Where did it go?
Some kind of chemical reaction.
No, it's not a chemical reaction. They like water molecules like ethanol molecules better than they like themselves. So they adhere more strongly, and then literally they compress together and make it more dense solution. How weird to think about. So what's happening here is these got the water molecules. It might have actually shrunk a little bit. Not enough that's measurable, but the water molecules adhere so strongly to the ions, it may have shrunk a little bit, but we didn't measure it. Same thing here, right?
There's a difference in density.
Yeah, density changes, right? But and we use density to identify solutions. So most of the time we use it for solids. But yes, density of the solution is one of the ways that we measure sugar content in a solution. Okay, so far what I've done is this. Calcium chloride, aqueous. Sodium carbonate, aqueous. We'll balance it too. So this is what I'm going to do. I'm going to mix the two together. We'll look at solubility rules. I'm going to pour one into the other. It doesn't matter which way you go, but let's see what happens. What happens? Looks like glue, huh? Yeah. Is that a solution? Is that homogeneous? No, you can't see through it. It's a heterogeneous mixture now. But there's, I mean, clear, clear, not clear, right? We made something new. That was a chemical reaction. One of the signs of a chemical reaction is you take two homogeneous solutions and you mix them together, and it's not homogeneous anymore. That's a precipitate. That's what we call a precipitate. And that's a solid. So let me ask you a question. Like, have you ever dissolved table salt? Like just salt. Put it in water and stirred it?
Yeah.
Is it soluble? Yeah, because you don't see, the salt doesn't stick around, right? People gargle with it and stuff, right? So that you know that this is aqueous. So this must be the solid. Just in principle, that's what that is. Now, it's not balanced. We'll balance it here real quick. I don't know which one to balance. Let's say this one. And so I need 2 sodiums, like that. And then that takes care of that. And then I'm going to do the carbonate. There's a carbonate. So I've done that. Oh, yeah. And how many calciums do I have on the left now? I have a calcium and a calcium. And 2 sodiums. 2 sodiums. So it's balanced. All I needed was 2, right? So kind of think of this. What I just did was this. I had calcium ions and chloride ions in one solution. So this is my chloride. That's my calcium. So that's Ca2 plus, and then Cl minus, like that. So those are floating around in the solution. In the other solution, oh, I gotta have different colored pens, huh? Let's try this. I had sodiums. And carbonates, which I'll make that color. And they're polyatomic, so I'll just make them bigger like that. And then I mix them together. And what happened? The sodiums, right? That's these guys. And the carbonates, I'll make that like this. Those guys, right? But the sodiums and the chlorides stayed in solution. That is, they don't precipitate out. So when I mix those two things together, I have all these ions mixed together, right? The calcium and the carbonate precipitated out of solution, that it made a solid. So it's going to look something like this. Now, we haven't waited long enough to see this. Wrong one. I'm just spending a lot of time drawing, aren't I? But they make what's called a crystal lattice. So it's actually making a solid where the oppositely charged ions are attracted to each other, and they make a regular sort of repeating pattern. I hope this thing I'm done. The reason I just leave it out is you stare at it, you don't see it all the time. I don't know if you can see it at the top. It's a lot thinner. That's because you made a solid, and solids don't stay floating in solution, they'll drop to the bottom. Okay? So it's actually more dense down here and clear at the very top. So in that solid, what you're looking at is this stuff will eventually make a layer at the bottom, calcium carbonate, which is it's the same as chalk. It'll be a white powdery substance, okay? And then in solution, above the solution at least, like in the top part, you're gonna have your sodiums, which I made green. And your chlorides, which I made red. Just kind of floating around in the solution still. Okay. One of the ways we separate things apart from each other, like we want to get a particular metal ion out of a solution, is we create a precipitate out of it and we pull it out of the solution that way. So impurities in water, drinking water, things like that, we can precipitate a lot of metals and then purify the water that way. So you're going to have to be able, this is one of the hard parts now, we're going to have to be able to predict. So stop zoning out. I know a lot of you zoning out. You have to be able to predict the products of chemical reactions. So I want you to focus on this part. This is in part why I took a break, so that like you know, go outside. Like these guys, they went outside and had a good time. I'll bring a hacky sack or something. These are the steps that I generally recommend that you do for predicting the products of precipitation reactions. So what you're going to be doing is you're going to write out all the ions of the reactant. And you're going to predict whether or not what the products are, and then you're going to write the chemical reaction for the reactants to the products. Okay, so we're going to write out the reactants as ions, we're going to predict the products, right? And you're going to predict it using the charges, just like you did, like I said, write the formula for this ionic compound. You're going to look at the charges, and you're going to write the formulas for that. The last thing you do to predict whether or not a reaction takes place is you look at the solubility rules. If it forms a solid, then you made something new and a reaction takes place, okay? So let's go through a couple of these, right? So for reaction one, you're gonna write it out as ions. And this is one of those areas that I saw on the nomenclature worksheet, as well as I've seen in the past, people struggle with knowing what to write for the ions, okay? So what are the ions in calcium nitrate? Say it. Calcium ion, nitrate ion, right? You just said the ions. So one of the things that you have to get yourself to do is say the name of the ions that you see and then just write that. So I'm going to write two things and you're going to tell me, actually you won't tell me. You'll just in your head say which one's right, okay? So for calcium, I'm going to write this or this. And then for nitrate, I'm going to write this or this. Now, I know some of you are thinking about this incorrectly, right? So look at the choices I gave you. For calcium, which one's right? The bottom one, because it's the ion, right? Not calcium, the element. So when it says, when I say write the ion, I want you writing this. Now for the nitrate, this is the one people struggle with probably the most. Which one of those is actually nitrate? The top one, right? This got added so that you could balance charge. It's not nitrate. It's just part of the chemical formula. So what you need to do is recognize when you say nitrate, don't write what you see in the formula, write what you know to be nitrate, right? Don't write NO3 in parentheses subscript 2 minus. That was all there to balance the charge.
So the steps, are we going to have to memorize polyatomic?
Yes.
Certain ones?
The ones that we did up there, and then there's a list on one of the pages on Canvas. Memorize. And there's a Canvas quiz, I think. I remember that you can just say, they'll give you an ion, and you have to multiple choice pick the name of it. Yeah. But yeah, that's why I try to teach you the trick. Like if you could know what the 8s are, then all the ites and the hypos and the pers, they all come off of that name. Yeah. Okay, so that's what calcium nitrate is. Now sodium carbonate. So when you say sodium, what's the formula? Na, right? Plus. So this is Na plus. So that's my I'm going to write it in red. That's Na plus. What about carbonate? And no subscript 2, no 2 plus, right? Just what you know to be the formula for sodium. Carbonate, CO3, charge, 2 minus, okay? Now, if you don't remember, if you know sodium's +1, then you know carbonate's got to be a -2, right? You can figure it out from the formula. So Ca, or Na, and then CO3, 2 minus. Now what we're going to do is we're going to write the formula of the products based on the ion charges. So calcium's going to go with the carbonate. Okay. Why did I say that? Because a positive charge and a negative charge will get together. If it goes together with the nitrate, then you didn't do anything, right? So we're trying to predict what happens if a reaction takes place. The sodium will go with the nitrate. Yeah. So we're taking basically when you're doing this, you're going to take this guy, put it with that guy, and this guy, and put it with that one. So you're doing the insides and the outsides. And then when you write the formula, the metal ion always goes first. So I'm going to write Ca, and then 2 plus and 2 minus, so it's just CO3, right? Plus Na, all right? And then what? NO3, yeah. So again, just write the formula of the ions, say the name, and then write the ion, and then do it's called a double replacement, where you just swap. My wife's analogy is, I have to preface it with that. It's like you go on a date with somebody, and then somebody else goes on a date with somebody, and then when you leave the party, you're taking the other person's date, and they're taking yours. I don't know. That's just weird, but I'm sure it doesn't happen in real life. So this is what we have. That's how you predict the products, and then you have to balance it. All right. So why don't we balance that? Which one do you want to start with? Something that has the most subscripts, that kind of thing. So I'll start with this guy. How many sodiums do you have? 2. So I need to have 2 here. So I'll drop a 2 into there. And that does that. And then I have to do the nitrates, right? How many nitrates do I need? 2, because I have, right, the 2 in front now. So I'll need 2 of these. And how many do I have on the right? How many do I have on the left? 2. So that's balanced as well. And it turns out I have 1 calcium and 1 carbonate. So that's also balanced. So it's all done. I just need the 1 coefficient. So my final formula would be this right now. Ca NO3 2 plus Na2CO3 makes CaCO3 plus 2NaNO3, like that. So now that's just actually for this question, it's just this. Predict the products, and we balanced it. Now it says use solubility rules to predict the states. So what did I say about group one? Group ones are always soluble, right? Aqueous. And nitrates are always aqueous, right? If you look at the rules going back, right? Always soluble, always soluble. So now when you look at this list, okay, go back to this, go look at this list. Calcium nitrate, what is it? Soluble, so it's aqueous. Sodium carbonate. What's sodium carbonate? Soluble, right? So aqueous. I'll write it in blue so it sticks out a little bit more. What about sodium nitrate? Aqueous, aqueous, right? They're always group one and always for the nitrate. So that's also aqueous. It doesn't cancel. It's not like negative charges, negative signs or something. So the only one you really have to look up in this list, if you can remember those two rules, is the calcium carbonate. So you go back to the carbonates. And what do you know about calcium carbonate? Solid? Solid, right? Because it's insoluble. Carbonates are generally insoluble, and calcium's not an exception. So we reduced four, a lot of times people end up looking up all four. If you can just remember those two rules, you ended up looking up one, right? So this will be a solid. So when a solid forms, right, this is called a precipitation reaction. A precipitation reaction occurs. Space on this one. Let me just. What happens if they're all aqueous? If they're all aqueous, it means no solid form, there's nothing new that forms, and there's no reaction. There's a lot of instances where we mix like ionic compounds together where we don't want it to precipitate out. And so they use solubility rules to figure out what combinations of like potassiums and irons and stuff like that they can mix together in a solution so that stuff doesn't just precipitate out of the solution. All right. Do one more. Maybe, yeah, we'll do one more. Iron 3 chloride. And then what I think I'll do is I'll save that one. Yeah. I'm going to do one example off each one of these, and the rest we're going to do kind of as a worksheet in class. It'll be like practice time. There'll be more lecture, but I don't want to lecture more than that today. So why don't we go ahead and do this one, right? And then we'll do the last one like a worksheet style. And I'll also show you how to do these guys. I'll show you the first one of that one and the first one of that one, and we'll finish them just as like we're doing a worksheet class. All right, so iron 3 chloride with aluminum sulfate. So what's iron 3 chloride? Fe3 plus. And chloride is Cl minus, right? What's aluminum? Al. And where is it on the periodic table? What group number is that? 3, right? So it's Al3 plus. It's one of the ones you can predict from the periodic table. And sulfate is SO4 2 minus. Yep. You already have it memorized just by staring at the periodic table, right? Yeah, that's good. So what goes with what? Fe goes with in the and the Al goes with Cl, yeah. And that's how I get my products. So I'm going to write the reactants and products, and then I'm going to look at the solubility rules. I'll start each one. You finish it. Then we'll balance it. So you can write the compounds because the cations will show up. The anions get written after. So what is it? Iron, and then write the rest of the formula. And then aluminum, write the rest of the formula. So Fe what? So, and you're making iron 3 chloride, so it's this and this for the reactant. So it'd be this and this for the product. Yeah, so like this guy gets together, so you can put it here. This guy gets together. And then for the product, you'll swap it. Look. That's cool. You could probably drink it and not hurt yourself too bad. It would be like drinking dishwashing laundry soap. Carbonate is used in that. When you have hard water, detergent. Right, I guess. So that, but this is a 3 plus 2 minus, right? You put parentheses around the salt. You want 2 of these. You get the charge to this here, okay? Yeah, but that's the right formula. And then do the same thing. Oh, yeah, so this is plus 3. Oh, yeah, 3 plus 3. And then so like the CL's minus 1. Alright, so it's on your right iron chloride and sulfur. So that's the reactants, because you don't have formulas for those. Oh, okay, so you're gonna write a reaction. Like this. Yeah. So you're gonna start with the reactants and go to the products. You have to write these guys go together. And then make sure you guys make it so the charges overall are 0. And talk to each other about these stuff. If you can't help each other, where are you at? Okay, and 3 is up, right? It's 3 plus.
Oh, really?
Yeah, the 3 is not the subscript line. So if you put this 3 plus with 1 minus, how many things do you have? I mean, that part, it's like this. if you want to make a compound out of these, the overall charge has to be 0, right? Yeah, so how many Cls do you need to make it 0? Yeah, so the formula for the first one is FeCl3. And you do that, and a lot of people do it just by taking the charges and doing that. Yeah, leave the signs out, but you cross those charges. Yeah. It's hard to believe that was So this is good. Yeah, but the 3 goes here. I'll be doing it in a second. The 3 goes down. 2. What's called crossing charges. Yeah, so SO4 for the reactant. Yeah, but then you have SO4. But the charges are, right? This is 3 plus and 2 minus. So to get it to be 0, you take it 2 to bring it down, or 3 for times. Okay. Then you're going to write products on the other side. So this is 2. So this is 3 plus. That's 2 minus. So think about the charge. Yes.
Yeah.
So what do you have to do with the aluminum? So let me work it through. So we did the iron, right? Now I'm going to do the aluminum with the sulfate. So this is a 3 plus and this is a 2 minus, right? So you want, yeah, you cross them. So you say Al, you're going to have subscript 2, and the sulfate, SO4. And the subscript will be 3. And the point is to make the charge 0. It's a compound. It has to have 0 charge. Now the iron is now I'm going to do the product. All right. So for the product, I'm going to do the iron with the sulfate. I'm going to put those together, and then I'm going to do the aluminum with the chloride. So those are the ones I'm putting together. Okay. So if I'm going to put the iron with the sulfate, you notice I have the same problem. I have a 3 plus charge here, and then I have the 2 minus over here. So it's going to be a 2 down at the bottom of this one. Oops, sorry. 2 here. And then I'll have in parentheses SO4, 3 like that. What's that? The aluminum? Yeah, it'll just be Cl3 because the aluminum is 3 plus, that's here. The chloride is 1 minus, so I need 3 of those. So it's FAlCl3 like that. So this one doesn't help you to know any of those nitrate group point. You have to look them all up. Okay. But you can look up chlorides together. So you have iron chloride and you have aluminum chloride, right? So we'll go look at the solubility rules for chlorides because those are together usually. And you'll see that it says right here, chloride, right? when any of these ions pair with silver, mercury, or lead, it's insoluble. So that means the chlorides are both soluble. So those are both aqueous. So I'm going to go back here and write that in. So this is aqueous, AQ. This is aqueous, AQ. And now I have to look at the sulfates. We'll back up to the sulfates. And there's my sulfates. What does it say, sulfates? Sulfates are generally soluble. When sulfate pairs with calcium 2+ and strontium or barium or lead, it's insoluble. So what do we have? We have aluminum and iron. So those are all aqueous as well. Okay. So this guy would be aqueous. And this is aqueous. Oops, I accidentally pushed a button with my hand. Let's close it out. Did anything new form? No. These are all just ions floating around the solution. So the ants, like for this particular reaction, right, no solid gets formed. So we say no reaction. And we usually, it gets abbreviated NR. So I'll write NR a lot of times. So not every combination of ions that goes together makes something. Sometimes they stay in solution. Okay. So what I want to do, I'm not going to do number 3, but I want to show you question 9. What we've done so far is we've done molecular equations. And molecular equations are all reactants and products as compounds. Yeah, neutral charge, cations and anions together, that kind of thing. Now, what we're going to do is write the complete ionic equation next. And so you need to have done the work we did before to write what's called the complete ionic equation. What does it sound like when I say write out the ionic equation? What's it sound like? Write out what? Everything is ions. Okay. But everything, you write out everything as ions as long as they're soluble. So you're going to break up the soluble compounds and write those as their ions. So soluble salts, that's what we're talking about, the ionic compounds, another word for ionic compounds. And strong acids we write as ions. Now, for the first reaction, just to go back and look at it real quick, this calcium nitrate reaction, right, and sodium carbonate. If I'm writing that out as an ionic reaction, let me rewrite it here. Na, calcium nitrate, and sodium carbonate. So I'll rewrite that equation. NO3, 2, that's aqueous, plus Na2CO3, aqueous makes CaCO3 solid, plus 2 NaNO3s. And that's aqueous. So when it says write the ionic equation, so that's from the page above. You could just draw a line up to it. You don't have to rewrite it. You have to write everything out as ions. That's aqueous. These are painful to do, by the way. I'll just tell you. They're very tedious. So I'll start it right here. Calcium nitrate, I have to write it out as its ions. So that's going to be Ca 2 plus. Now, you should write aqueous after every single one, but I'm going to teach you my shorthand for it, and you're welcome to use it as long as you know what it means, okay? Plus 2NO3 minus, because it's aqueous, plus Na plus, but there's two of them, plus CO3 2 minus, and then an arrow. Now, calcium carbonate's a solid, so we leave it together. CaCO3 solid. And I don't have enough room, so I go plus 2Na plus 2NO3 minus. Now, technically, every one of those ions has to have an aqueous behind it, okay? So what I always do is I just do this. I make a blue squiggly line underneath it because water is wavy. So that's, to me, is my symbol for it's dissolved in water. So rather than write aqueous, 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 because you do that a lot on these, and they get to be like twice as long by doing that, just put squiggly lines underneath it. Or write at the end, all ions are aqueous, because that's what they are. Don't write it over and over again. The online homework for this, by the way, you have to type them all in. Oh, it's ugly. That's why I stopped. One of the reasons I stopped using online homework. Okay, last thing we're going to do is we're going to do the net ionic equation. So, yeah, so there's this thing called spectator ions. The spectator ion is an ion in solution that doesn't do anything, okay? So that's like the same, like the term we use like when you go to an athletic event, like basketball game. Unless you're playing, you're a what? You're a spectator, right? So you're just sitting there watching. You're not actually participating in what's going on in the game other than you're yelling and screaming and all that stuff. So this is what you do in a net ionic equation. You get rid of all the spectators, okay? So if you look in this reaction, right, everything in the product did something. Those are not spectators. So that means the calcium did something and the carbonate did something. But you notice the sodium and the nitrate. They didn't change. The sodium ion in the reactant, it's sodium ion in the product. Same thing's true with the nitrates. Nitrate ions in the reactant, nitrate ions in the product. So the net ionic equation for that is just what's left after you get rid of the spectators. So it's going to be Ca two plus an aqueous, right? Plus CO3 2 minus, that's aqueous. CaCO3 solid. Like that. That's the net ionic equation. A lot easier to write. The reason net ionic equations are important, they tell you that if you mix calcium and carbonate ions in any form together, they'll precipitate out as a solid.
When you write the net ionic equation, does it have to be equal on both sides?
Yeah, balanced. Yeah. So this one's balanced. And the way I did the total ionic equation, you know how I kept it balanced? I used coefficients. When you cross everything out, it should still be balanced at the end. Yeah. Okay, so this is what we're going to do. You're going to do reaction 3 up here. Do the reactants and the products, and then write the states. And then you're going to write the complete ionic equation, the net ionic equation, then we're done for the day. Okay? Get the lights turned back up. And I'll leave this on in case people have questions I can write. Good dinner, guys. More coffee in the morning.
Hey, which one did you say you want us to do?
All of them?
All starting with this one?
Yeah, do that one, because we already did these two. Do that one, and then on the next page, you'll do those again. Yeah, and NA plus. She has some of this to memorize. That. Handy. Oh, yeah, look at color. I guess everybody can do that.
Yeah.
Be one of the cool kids.
It should be. Let me see. For the modules.
Wait, is it the list? Yeah. Look at pages.
And the 16 for
Look, there's like a billion things.
So I just screenshotted it. So my prisoner.
Oh, you took it. That's a screenshot.
Yeah.
That's a much better way to do it, actually, because otherwise it disappears.
Yeah, and it takes me too long to find it.
Any reference material, though, there's two places to look in the module under the exam, for that particular exam, and then on your pages. The homework's there. Other things you can find. We can get it. You get it on your phone.
What?
On your, when you like the Apple Watch. Can you like make it show on an Apple Watch?
Yeah.
That's dangerous.
I should have said no.
No, I think you probably could.
Super small.
Yeah.
It's gonna be so ugly.
You have to zoom, go like this a lot.
No, you can't
It'll
even
be
zoom
kinda
into it. You're just.
Really?
You look
Jeweler's watch glasses. Yeah, yeah, minus one. Yeah, so OH, O is 2 minus, H is plus 1. And so that leaves you with minus 1. Any questions, raise your hand or something. Shy. That's right. Yeah, so you're gonna have, this is your products, right? And then you have your reactants, so you have to write those out, so you balance. You're almost there. So, they're all mixed up.
How do you know which one it equals to?
This one's solid too?
This sounds like these are all broken up, and it's just one. Those are just. Hey, I have a question.
Yeah. Sure, yeah, scan it, so I get it back.
So for
This
this,
solid,
I
it's solid.
don't know why I know that. Actually,
Solid.
the wrong one. Oh,
Which one?
this. I'm confused. So you know how for this you only wrote down one?
Yeah, this is solid.
Yeah. So then what do I write down?
Oh, no, I wrote these here.
Oh, you wrote both of them? Oh,
Yeah,
oh,
I just read it, I
okay.
couldn't keep writing,
Okay. So then why'd you keep these together?
because it's a solid.
Oh, so then I still have to break them apart because it's all.
Yeah, if it's aqueous, you break it apart. If it makes a solid, you leave it together. Yeah, yeah. Yeah, but how do you do it? What's not that bad. They just start with either this or this, and work. There.
You still break them down. Either of these are salts. And so this one's the actual one here. That's this one. Being crossed out. Yeah, because it was salt. So salt. So that's C here. This one. Yeah, because this one's made up of all liquids. Yeah. Yeah. Oh no, here. Because this is 3 plus, right? And this is 1 minus, right? So how many? 4 in this thing? No, as the reactant. So when you're writing this as a reactant. This is 3 plus. Sorry, I should have put it. This is 3 plus, this is 1 minus, right? So how many? Does that formula look right? Are those subscripts in the right place? So
Oh no, that's MCO.
Yeah, that's why you can't balance it. That's what I was saying before, that like when you write the formulas, when you can't balance it, go back to the formulas because there's probably something wrong with the formula. Okay, so which is this? This is. Versions. To do that one, I guess. That one. I have four. I have four people missing. I have 5 examples.
San Francisco.
Huh?
San Francisco.
Oh. Oh, I see 6 examples. Look for you. Yeah. Die. That's not NaCl. It's plus 190. To balance this, you did it 3 times. The parentheses around here, that's a 3 plus. That's 3 plus, right? Yeah. That's 1 minus, right? Yeah, with parentheses around the weight, so you actually have OH.
Oh, that's not right. So we have
I have no idea if I'm doing this right. I'm confused.
so which one?
It's a good thing I get the 8 with 3 swapped. I had a heart attack.
Is this right?
Yeah, and you don't have to, if there's just one, you don't have to put it there.
Really?
Yeah, if there's just one polyatomic ion. That's what's hard about them. You don't recognize them in formulas because they don't have parentheses sometimes. Yeah, that's hard.
Okay.
But yeah, no, it's generally you don't do
It
that.
just looks so weird, like next to each other like that.
I know. I can't do anything
I was like
about
looking
that.
at it, I was like, this does not look right at all.
No, it's right. And I wouldn't mark you wrong for that. I would just tell you to fix it.
So just NaOH.
Yeah. Ooh, that though goes on the inside of the
What, this?
tree. Yeah. That parenthesis on the inside because you have 3 H's, not 3 O's.
Oh.
Ha 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 ha. No, it's not bad. Yeah, it's fine. I have 6 children. All done. Does it change right now on your phone? Weird. Usually things don't work that well. Usually you're like it says it's not there anymore.
No, I think it's correct now.
That's
Don't
right.
pay attention.
That's right. Except
But that means, oh, this 3 means that there's 3 of on the hydroxide.
Yeah. You only need 1 of these. 3
But-
hydroxide. 3 is just
Oh,
for
that
the
means there's
parentheses.
already 1 there. Because this 3 also changes.
And then everything else is yeah. Yeah, good. Good. And my recommendation, guys, is you always go home and do homework right after. Some of you like that job.
Oh, yeah. I don't understand. My brain hurts.
Oh, this.
Yeah, you put it down right there. So like, oh, wait.
That's the abbreviation for one of the
Yeah.
Then this one, if you actually write out, if you write that out, yeah, you're done. Here.
My brain is fried. I can't do this one. I give up. Where's ECL? Name?
Should make F2 FECL.
I'm gonna right here.
But you put these numbers in front.
Leave home for shit.
Oh, yeah. So you got yourself confused by doing that. You got 3 inside there instead of something. That's what that is. Okay, formula. So. Oh, you can leave parentheses out. It's only for the sheet out. Nope. That's fine. You can leave it in front without the parentheses, because there would be 3 options. There's the thing, what do they call it? Test yourself. Okay, yeah, close. On the formula, you need parentheses around if I see that,
Let's see.
Oh my god, I think I balanced it.
these all cancel, right? You notice that everything's canceled. Yeah, good.
Yeah.
Reaction, yeah. That way you keep track of all the reactions.
So then we're.
Yeah, she was.
This being it.
Yeah. Yeah. And the three tells you there's three of them. Right. Negative. Well, there's three of them. So, writing out. Yeah. When you're writing it out, it's
So it's
yeah.
This one also has
Yeah, it is. When you're writing out, like this is telling you there's three of them. So you're writing where the ion, write all that stuff.
Yeah.
You done? You done? Anything else from Dr. Not really like opposite, but I had a student text me said they needed help. So I told them. Yeah, I'm not sure. But this one. Yeah. So that's sodium, that's hydroxide, that's correct. This is iron, this is chloride. You don't have a chloride. So then when you write the formula, say, so you understand when I say the Pittsburgh process.
Oh, okay.
Yes.
I didn't bring it on.
Balance. So take 3 pluses, and put 3 minuses. That's 3 pluses here. The 3 down at the bottom. That is 3 of those plus 3 minuses. We don't talk about the 1 down here usually, but really there's only 1 it's a minus. That would be 1. So you have 1 of these. So you have 3 pluses. Here it's 1 and 1. So you stick with that. Then when you do the products, what you're going to do is you're going to do this. You take the iron. Then because you don't want to, you put it back with this one. Yeah. So positive charge. So they don't like it. They always, compounds always pick the opposite. It's not so that's why chemistry. That's physics. So these pick the opposite charge. So then this. So this, and I always start up in the positive and point negative because this is first. Now you want to write the formula. many?
3 CM minus.
Yeah.
Every plus one.
So that balances the charge.
3 plus POH.
And then the next one is anion. No, it's not balancing.
Or not?
Because the balancing is after you write. Because how many CLs do you have? But this is balanced. The equation. Yeah. The lab has people get confused because we've been doing balancing and writing equations, and they get to this point and think, well, it's not balanced, so it's not supposed to be balanced. So we'll do that next. Then there's Adam who writes the formulas and balances. Is that what you're doing? I think that's what you do.
I don't know what I was doing. Maybe I was doing that, and then I got to the end, and I was like, I don't remember anything what you said.
Are you straight with that now?
Nope.
Nope.
Now I'm just firing off. So
I'm sorry for you.
I combined them, and I had a subscript.
Yeah.
Okay. And then what? Rebalance that?
You actually write the reactants out. Yeah, so the products. Right? So you have reactants and products, and then you balance.
And so
So you're balancing
when
two
I'm
things.
balancing,
Balancing
I'm not adding a subscript on balance.
Yeah.
I'm adding so it's going to be like 3 of these, like 3 CL.
Yeah. So write out the reactants and the products.
So that's what I did before. So then I can keep back of this.
Yeah,
And I change this to 3 CL.
Oh, yeah. Right. It's going to be FeCl3.
So Fe 3 plus.
Still have to write the formulas.
So rewrite the whole thing alone.
Yeah.
We're doing that last part.
Wait, is that one you're working on too? It's one she's working on too. Okay. This one. All right. So what I just walked her through, she wrote out all the items. And then to write the reactants, you take this and this, you put it together. And you want to make sure that the charge pluses and minuses total balance out. Right, so it's FeCl3.
Right.
And then NaOH. OH for the reactant.
3 in AOH?
Well, it's not balanced.
Oh, I'm sorry. Yeah, in AOH.
And then you have iron with the other anion
Iron with.
with hydroxide.
Yes.
You got 3 with this. Yeah?
Yes.
And then sodium chloride.
Oh.
Because there's one that's positive, it's negative. So they just,
These are if I wrote it down before.
yeah, it's ordered it in that. So then you have to balance it. So you have 3 here. Okay. So I'm starting with 2. There's 1 iron, so that's good.
Wait,
Yes.
isn't there 3 iron on that side?
There's 1 iron because the subscript is just to what's to the left, unless it's parentheses, and it's everything.
After I balance it out, so this guy.
What's your class at?
That's communication right over here.
But
It's
it's
over at 12:51.
Not as long as this one. I'll be around, so if you text me. I'll be around at probably 1:30.
I'm gonna finish the homework too, because I did it.
Oh,
Where it said chapter 5 and chapter 6, I did it all.
right.
I didn't know they're doing that chapter. No, that chapter 5. And that's, yeah, I missed that one. I have to redo. I only saw the chapter 6 under chapter 6. I didn't see that chapter 5 had a chapter 6 in either. So I'll find you later.
And if you can't find me later, give it to me on Thursday. I'm behind. I'll probably grade it after Thursday, so if you bring it on Thursday.
I only have one problem left to do. So.
That's it. Okay, where are we at?
That. Oh,
Yeah.
Right. So then to balance out.
you bring this guy to this side, right? That's the only way.
Because there's 3 OHs here, you need a 3 in front. That makes sense?
Yeah, review.
Yeah, because you have 3 here, so you gotta have a 3 here.
Yeah, because once you like distribute it, like you said, like it distributes to that guy, so now you did it correct.
And then the OHs will be balanced, right? And the sodiums will be balanced. And then you look here, the chlorides are balanced. That last thing has to balance. If it doesn't, your formulas go back to formulas. And I like this bouncing back. I don't know what it's called. I like that. This is how I look at it. And I didn't learn like to do that. I didn't learn that. I learned it in college. And I really thought I had chemistry, which I liked it. I did very chemistry. It taught me a lot, but it wasn't chemistry. So I got to UC Santa Cruz, and they stuck me into the second quarter of chemistry instead of the first. So all of this stuff, all the basics, the balancing reaction, stoichiometry that we're going to be doing, all the protons, neutrons, electrons, all that, I didn't know.
You have to pick up on it pretty much as we were going.
I hated chemistry so bad when I got to Santa Cruz. I have no idea what this is. This is so confusing. It wasn't that I hated it, it was more like I just completely was lost.
Well, how did you get lost in the first place? You canceled the shit?
I
It was a
know.
period,
No,
I
because
guess.
I took high school chemistry, it was assumed like if you took high school chemistry, you must have had a certain amount of background that you start the hard stuff. I started in the hard stuff. Second semester, basically. Second semester. Right. But, you know.
This is not beginning chemistry.
It
is?
Kind of.
It's pretty overwhelming, but this is the beginning.
This is the beginning. I should have had this class before I took college. You had a college picture that stuff. I should have finished this class. And I could have done it. And that would have been fun.
Right.
But I went straight into this other class.
You intermediate right away.
Yeah. Just like, what?
A lot of the foundation just wasn't laid out, so you had to
Yeah.
figure it
I
out.
had to figure it out.
Like they
I
already-
had good friends and drank a lot of beer.
There you go. There you go.
That's all I'm going to say. We made a party out of it. And I probably shouldn't say that.
What? You said
That's
what?
why it's like nowadays.
That's how, that's, you know.
Tradition doesn't really change.
We didn't like drink. Yeah, we just,
The word,
yeah, it was
that's a caffeine.
it's light.
Right.
And then, you know, for example, study hard and stuff. There's a lot of crap. Yeah, that's what life is. Lots of hours. Okay. But I did get better at it. I like this stuff. I know that. Imagine like starting this. That's where I started.
Yeah.
And I was past it. I didn't even know like really react to some products. Just shut right.
You passed the class.
Yeah. I had good friends, like I said, good friends who studied a lot. They went to schools that prepped them well. And said, oh, you just do it like this. Okay. I'll do it like that. And then I TA'd this class like the next year. Oh, wow. Then you read it. Okay, so here, we have all the study on this. So we're going to go to the molecular. This is the molecular, we're going to go to the ionic. So to do the ionic, just basically have all these ions. You work it out that way. So you're going to write everything in here is ions. Everything here is ions. Now this is, when you look at the solubility rules, you look at the solubility rules of this. Hydroxide, right? Hydroxide generally is soluble. So it's a solvent. And it's not an iron's not an exception. So for this, that's an S. And then, but everything that's group one, like the sodium chloride, that's a everything group ones. Acid, sodium, lithium, rubidium, all that stuff. So it has a nitrate in it. Is it? Just knowing that. So you didn't have to. They're both that group one. Now, we do this part. We want to write out this is basically undo everything except for the one that's the solid. The solid is going to stay like this. But all of these will be broken up into their ions and still balanced. So for example, you take this when you break it up, you have 3 sodium ions, 2 chloride. So you go ahead and do that.
So this is where we're gonna have three.
That's this.
So are you writing it out like?
And a bunch of ions.
Like broken down,
Yeah.
like one by one.
So like here, right? And we'll start with this one. So you have 3 sodium ions. And that's why it's nice to have minus you go through, right? And then 3 OH minuses plus, and then this is 8 Fe3 plus. There's 3 Cl minus. And here's to the reaction. And then you write this. Because it's a solid, you don't break it up. That's like in the beaker, it's the precipitate. You see the beaker, you like orange, yellow, solid. It's like almost like it's like gel. And it compresses and dust.
So I noticed when she wrote the CL is written different. So
You see?
I wrote it incorrectly.
Oh, I guess it was right. Oh. So no, you're writing it just like you have. Because remember how you got this subscript is by doing the crossing charge. So it's 3 in front and 3 on.
Oh, we already.
Yeah, that's what we did. We put it in front.
The subscript only got to the ion formulas because you're using the balanced charge. And so you just leave them off. You just write the ion.
So for all of them, 3 goes over here?
Yeah, the 3 is in front.
It's almost like you're telling him the count of what you have.
Yeah, well, it's the balance form of the ions. You just wrote the ions. Yeah, it's that. It is the count. It's the balance.
So you're just like,
Finish
write
it.
it down with that.
63D was easy. Just multiply the carbons by 8.
Oh, yeah, take 1 divided by that and multiply. Yeah, I remember that problem.
So for the homework, like you know how like going on tangent, you know how you were in one like let's say it's chapter 5 and chapter
So here's like,
yeah.
I didn't see this. This is why I didn't see. Because I started on the check. So I was like, there's nothing. But it's like, yeah, these are the ones I only did what was for this chapter 6. I didn't see this chapter 6. Yeah,
Oh.
chapter 5.11.
And then it was really fun.
Yeah, so hang on. So chapter 4, right? And then we covered up through all of this material, right? That previous week.
So it should have been conjoined on one assignment.
Yeah, I think that was with the previous side. I don't remember how it breaks it. Maybe I should have just had you turn 5 and 6 together. Because that's where it gets weird in the book. Previous editions were split different materials. That's why it's kind of hard. But this is the stuff that's due this week.
I think in all of this and these, and then because I didn't see the 5, I
This is part of what we heard last week, right?
yeah.
So basically, I think what I said before when we finished this, I think we did up to like this problem here in lecture.
When you did chapter 5, you said not to do 5.11 yet at first. We only did 5.7 and 5. These two.
Yeah,
And then after we finished, you said, okay.
then the
now,
rest of it, right?
Just 5.11.
Yeah, that was for one day. And then this was what was last week.
So is it wrong if I can join all of chapter 5 into one assignment and then chapter 6 into all one
That's
assignment?
fine.
Because I can join it like as a chapter.
Yeah, that's fine.
That was my big.
I'm not too picky. What I'm really looking at, just so you guys, I say this all every Thursday. I'm looking to see that he did the problem, and he corrected it, and then wrote out the precipitation.
And box it out.
Yeah. As long as you're getting the chunks done, that's all I care about. And you get it all done at the end, that's fine. But don't say, well, I just feel like doing this problem and this problem, and then I'll be done. Then
Oh, what are you doing?
actually, that's part of the lab.
Oh, okay.
We're going to do that next week.
I got scared because some of that sounded familiar.
It is familiar.
And I was like, oh, shoot.
Yeah. But I didn't talk about it in class yet. That's part of next week's lab. And then this is all of this week. All of 7. And then 8 is next week. And then it's kind of okay, because this is like, so this is the part where we decide, no, I don't want to talk about this in this chapter. Yeah, it gets really confusing. But this, for sure, next week's. It's actually called the formula this year was plus this. Okay, so we're here. Yep, and then you have to have the charges, so that's minus, plus. So minus. Okay. And it's not random how I do this, it's literally that, right? You wrote out these lines. You use them to write the reactants and products. You don't change them. These formulas with the coefficients in the front, not subscripts. The subscript are for the formulas, but for the equations, it's all coefficients. Stays balanced. So we're basically pulling the sodium chloride apart after it's on. So then when you get down to here, right, this is the solid, and then the rest of these are aqueous. Rather than trying to get all of that. You just get rid of things that aren't. Here's your product, right? And then it's the solid. The iron is in there. The hydroxide is in there. There's the sodium ions here. And chlorides. Just 3 on the side. So you just get rid of those. You write it just like I did here, right? Like the product, and the calcium and the carbon. And then everything else was aqueous, so there were all the other aqueous that are not in the product. Yeah, the stuff is not doing that.
It only goes to this one, like this. It's only here this, but it's here.
And then you will save it.
So should we
Yeah.
the coefficient?
This, yeah. Oftentimes, there's only 3 things in that equation. 2 lines that go with it.
Yeah, like where do we determine? I think that this is where you write the charge in. Correct? Good question. But that's when you finish the ending.
Yeah.
This 3 is for OH, right? But that means it's also for FE, right?
No, it's only for what's immediately to the left.
Oh, okay, so this 3 is only for fluorine.
Yeah.
Oh.
Yeah. Defense.
That's the hard thing for me. It's just now you trying not to distribute every little thing.
But it-
Think like math, right?
Yeah.
Math.
No. If you do your math that way, your math is right. Look at friends.
No.
If you had this, would you multiply the first 3 by 3?
Well, that's that wall barrier. That's what.
And everything in a chemical formula is plus, unless it's a parentheses. Put both of those plus together. So So this would be like Fe something, right?
So, for example, this is on your favorite criteria So, like for example, here's a perfect example. Like right here, what we're saying is that distributes to the hydroxide.
Yeah,
But it
Only,
doesn't-
right?
Only, but it doesn't go.
right, because this is plus, plus, plus.
And because this is great.
For parentheses, that those two are together, so everything in there.
So it's only what's in parentheses, not directly out of it. Okay.
You know, we're gonna finish this on Thursday.
Yeah, there's a lot left.
Yeah.
The last bit, I'm gonna say you read it, let's see if you think that's up.
The last bit.
Yeah, the last bit is just this,
Or like the last section, which would be eliminate
reaction classifications by types. Like, I'm gonna do all this stuff, right? But this reaction classifications by type, you could read this.
Oh, reaction.
Like, I'll talk a little bit about it, but precipitation is what we're talking about, like right now. Or we're talking about acid base. We're doing gas, evolving gas evolution. We may do some redox and then combustion reactions. Then we're going to talk about these. That's what these papers are. Right now, we're learning how to write equations, balance equations, types of equations. Right? But then there's a lot. Besides that, there's classification. This is precipitation. Two aqueous solutions mixed together. Solid precipitation. But then when you mix an acid and a base together, right, they do a reaction. But the predicting of the products is exactly the same. The atoms and the elements are redox are not easy. Gas evolving reactions are like precipitation reactions and acids. The reactants. Combustion is always hydrocarbon oxygen. Always carbon dioxide water. So we're going to talk a little bit about this. These ones, this is all reading. In the back, it says this is make two things to make one. That's synthesis. Make one thing, make two. That's it's not science. I might talk about this.
And we need that and dollars for Thursday.
Yes, it's the chemical formula you need it for. Magnesium or calcium. Basically, or oxide. Use the masses that you measure to get what it's. Pretty straightforward. That doesn't always get the best numbers. We'll see. Yeah. Your book has this giant. It's like this big. This is the only one. So it's giant.
Out of the book.
Oh, shoot, who is this? Hello, start. My mom's got a phone call. I got to render her house. Yeah, I'll be here. Sure, actually, I got
Next one. I thought it was more last. I don't know. They're not showing it.
Hopefully they're like busting the door.
Yeah, oh, yeah, this.
That's what I'm.
Yeah, I'll be here. Available.
Yes, so we do. Yeah.
So I'm not leaving, guys. I'll stick out around here if you guys want to work on homework or something.
Okay. No, I mean, I know. Oh, I walked out. You wouldn't even walk.